Hi everyone, this is week 3 and we will be covering differentiation tools in this week. We will first learn how to compute slopes by using the limit definition. And slope is the same as the first derivative of a function. Then we will define the first derivative through the limit definition. Then we will create equations of tangent lines, and then we will just start to move to differentiation rules. This is the content of this week's problem solving session. So look at the first example. In this first example, we want to find the slope of a given curve at the indicated point. Before start solving this question, let me remind you something. Okay, let's put a very quick recall here. Let's say this is our curve, y equals f of x, okay? And I want to draw a tangent line right at this point. You know, tangent lines are such lines which touch your curve at just one point, right? This is a tangent line. Let's say this point is A. And now I want to find the slope of this tangent line. Okay, how can we compute the slope of it? Slope of tangent line to our curve y equals f of x at which point? At x equals a. Okay, this geometric concept can be connected to the limit. Okay, this geometric thing has a relation with the first derivative of the function. So what is the slope? How can I relate it to the first derivative of the function? What is the relation here? So the slope of this tangent line drawn to your curve at x equals a is given by the first derivative of your function at a. Sorry? Yes, f prime of a gives us the slope. This is the first derivative evaluated at a, and it has a geometric meaning. It gives us the slope of the tangent line, and we will define the first derivative by a limit here. Limit as h goes to 0, f a plus h minus f of a divided by h, right? This is the limit definition of the first derivative. Okay, we will be using this idea to compute the slope in the first exercise. Okay, 22, let's solve this one. The function is given, and I want to find the slope of the tangent line to this curve at this point. So what I want is slope of tangent line at x equals 0, right? 0 is the given point, so I am supposed to compute this thing, and this is given as the limit, just like this one, f 0 plus h. Okay, 0 plus h minus f of 0 divided by h. Okay, we need to compute this to find the slope. Okay, what is f of h? F is given here. This is our function, f of x. So f of h is, in fact, h minus 1 divided by h plus 1. What is f of 0? You can easily compute it by inserting 0 for x's here. What is it? Minus 1 over 1. It is minus 1. Then we can compute this limit easily by doing these computations here. Okay, what we have, h minus 1 minus makes it a plus. So plus h plus 1. So I am writing this thing over a common denominator. Okay, that's what I did here. Divided by h plus 1 times h. There is also another h at the denominator. And then you see this is a simplification. So what we have, h goes to 0, 2h divided by h plus 1 times h. Then you can simplify these two, and then you send h to 0 to find the result of the limit as 2, right? This is the slope of the tangent line drawn to this function at this point. Okay, that's it. The slope is computed as 2, slope of the tangent line at x equals 2. Any question about this solution? Okay, then let's move on. The same type of exercise, but this time we also want something more. We also, after finding slope, we also find the equation of the tangent line. Okay, let's do that. Let's start with computing the slope of the tangent line. Drawn to which function? Let's choose this one. At x equals, you see the point is given as 8. Okay, how do we compute that? This slope is the first derivative evaluated at the point 8. So the limit definition goes like 8 as h goes to 0. Instead of a here, I will insert 8, right? 8. So 8 plus h minus f of 8 divided by 8. Okay, now let's use this definition of the function. This and this will be evaluated according to this definition. Okay, let's do that. Limit as h goes to 0, square root of h plus 1, I should write, right? Instead of x, I write 8 plus h, and instead of x here, I will write 8, like this. Then, divided by 8, okay, what do we have? We have limit h goes to 0, square root of 9 plus h plus, sorry, this is minus. I just turned it to plus suddenly, which is wrong. So minus 3 divided by 8. If you insert h equals 0, you will notice that this limit is an indeterminate form in this form. How to get rid of this indeterminate form? We did such computations last week. How can I compute this limit now, which is an indeterminate form? We can multiply and divide by the conjugate of this expression, right? Like that. Okay, and then we will see what happens. Limit as h goes to 0. This is in the form of a minus b, a plus b now. So a square minus b square, and then I will write the whole thing at the denominator to here. You see we start having simplifications. H's are gone. So the result is, I think we are ready to compute the result. What is it? We have just one at the denominator, and at the denominator we are assigning h to 0. So square root of 9 plus 3. So the result is 1/6. This is what? This is the slope of the tangent line. Remember, we start by this expression, slope of the tangent line. So this is our slope. Now I am ready to construct the equation of the tangent line. Okay, equation of tangent line. To construct this equation, you need to know two things. First, the slope is known as 1/6, where we computed by using this limit definition. Second, you also need to know the point, okay? Point. What is the point? As it is given here in the statement, 8, 3. Okay, then by using these ingredients, you can construct the equation of the tangent line like this: y minus y0, slope times x minus x0. So let's put the information inside this equation. By the way, this is the y0 component of your point. This is the x0 component. So y minus 3, x0 is 8, slope is given as 1/6. Like this. This gives you the equation of the tangent line. Okay? Any question now about this solution? Do you have any questions?
No, teacher.
Okay, thank you. I assume that if you have any questions, you will tell me. That's why I'm just moving on.
Can I take a screenshot, teacher?
You can for sure, but do you know that I am uploading this lecture notes as a PDF file also in OneDrive. You already have them as a PDF file in your OneDrive folder. You don't need to take a screenshot, in fact, but if you like, you can.
Okay, teacher, thank you.
Okay, you already have all the lecture notes in your OneDrive folder, even before the lecture. Okay, let's look at this one. This time, we want to find the points on the curve on which we have horizontal tangents. What does a horizontal tangent mean? Look at this visualization, please. This is our curve at x0 and x1. If you want to draw the tangent line, you will obtain such lines, which are horizontal, right? And there is a very special thing about horizontal tangent lines. Their slopes are 0, okay? This is the slope. Their slopes are 0. Since the slope is 0, this geometric thing is directly related to the first derivative. So the first derivative of your function will be 0 at x0 and x1 point, okay? Where this is your curve, this is our f of x curve. Okay, so what we want? For 23, we want the points on this curve at which we have horizontal tangents. So we will search for the points where the tangent line is horizontal. So where the first derivative is 0. So we start by computing the first derivative function then by using the limit definition, right? Okay, I will use the limit definition here to compute the first derivative. X plus h minus f of x divided by h. What is this one? In 23, we have this, expression for f of x. Instead of x, we will be writing x plus h. So let me write here. So x plus h squared plus 4 times x plus h minus 1 minus f of x itself. X squared plus 4x minus 1. Okay. This part is fx plus h part, and this part is f of x. Then we have this denominator. Okay, now we need to do the computation. Take the square. It is x squared plus 2xh plus x squared, multiply this, 4x, 4h minus 1, and then this part like that. And let's check now if we have any simplification. Minus 1 plus 1, gone. Minus x squared plus x squared, they are gone. Minus 4x plus 4x, gone. So what we have next? Limits as h goes to 0, I will just take h out, 2x plus h and plus 4, I think, divided by 8, and then you simplify these two. Now we are ready to give the result. If you send h to 0, what is the result of the limit? By the way, since we are expecting a function, it is totally perfect that the result of the limit depends on x, right? So what is the result here? Which will be the first derivative function? You see it. What is the result?
2x plus 4.
Exactly. So the result of the limit depends on x, which is what we expect. So this x-dependent value expression is the first derivative function for us. Now what we want? We already obtained that the first derivative is given like this. We want to find the points for which the first derivative is 0 so that there is a horizontal tangent there, right? Okay, so we want to solve for this first derivative where it equals to 0, so then x is minus 2, okay? If x is minus 2, what happens? First derivative is 0. So the slope is 0. First derivative is the same as the slope. If the slope is 0, you have a horizontal tangent. So that's the solution. Let me visualize it for you. So I think the graph of this function, x squared plus 4x minus 1, it has such a graph. F of x is x squared plus 4x minus 1. it is a parabola like that. And at the point x equals -2, okay, let's draw it like this. At the point, I don't want to insert x and y coordinate, but what we know is here, this is the -2 point. If you draw the tangent line there, you will obtain a horizontal one. Horizontal tangent, that's why the slope, which is the same as the first derivative, is 0 there. Okay? By the way, by using the differentiation rules, you can compute the first derivative function very fast if you don't want to use the limit. I mean, by using the limit definition, we obtain the first derivative function like this. And soon enough, in 20 minutes, we will start using the derivation rules. And I think you remember the derivation rules from high school for this function. You take the power down and you subtract 1 from the power. And similarly, 4 will be the derivative of the second expression. Derivative of the constants are 0. So in fact, by using the rules, the same first derivative function can be obtained very quick. But for now, since I haven't given the rules to you yet, we are using the limit definition to find the first derivative function, okay? But after we cover the derivation rules, we will start using them, and finding the first derivative function will be much more quick then. Okay, any questions? Can I move on? Okay, let's move.
Yes, teacher.
Thank you. So this is the next exercise, and as you noticed, we have stars for 32 and 34. I put those stars on purpose there because these are very nice exam type questions. You should listen to the solutions of them really carefully, you know. Okay, so f of x is given as a piecewise defined function. And the question is, does the graph of this function have a tangent at the origin? Okay, how can we understand this statement like that? So drawing a tangent line is related to what? Its slope is related to the first derivative of the function, right? So to be able to draw a well-defined tangent line, the slope should be well-defined. And for slope to be well-defined, your function has to have a well-defined first derivative, because slope is the same as the first derivative of your function at that particular point at the origin. So asking this question like that is the same as asking if the slope, okay, let me write. It is the same as asking, is f differentiable at the origin? And this is the same as asking, is this thing exist or not? Okay? So first of all, we need to understand the statement. The statement asks that, is the given function differentiable at the origin? Because only it is differentiable. You can talk about the first derivative, you can then talk about the slope. This is the same as the slope. And if you have a well-defined slope, then you can talk about the tangent line, okay? That's why we will search for this, whether this exists or not. Okay, before we start solving this question, I want to make some recalls from the recorded lecture videos, okay? So, recall. Because, you know, this is a very famous function. It has very strange properties. That's why it is famous. So I want to make some recalls on that function to you. Y equals sine 1 over x, okay? So do you remember how to graph this function? Since it is a sine function, obviously it will take values between plus and -1, obviously. I think from the lecture video, you remember that this is an oscillating function, but it behaves like crazy around origin. Around origin, it has very wild oscillation. So this is the craziest part of this function. Let me try again. So when it gets close to origin, it behaves very wild. It starts to have very wild oscillations. That's why I am telling you that this is a very famous function. Because of this wild oscillation around origin, things may get complicated at origin, like continuity, differentiability. Let's try to remember them. Okay, at the origin, does this function continues? And as I said, there is a wild oscillation. This function behaves like crazy around origin. Since there is this wild oscillation, let's now think about the limit around origin. What do you think? Does this limit exist or not? Since we have infinitely many oscillations around origin, your function gets closer to +1 and, sorry, this should be -1 and -1 at the same time. There is a very infinitely many oscillation. It jumps from +1 to -1 infinitely many times. That's why there is no unique number to which your function approaches. That's why this limit does not exist, okay? Because of this wild oscillation behavior. If limit does not exist, what can you say about the continuity of this function? What about the continuity? Obviously, if there is no limit, your function cannot be continuous there. Not continuous at x equals 0. Okay, we understand this, right? Now, look at our function. Our function is x squared times this. So step by step, I want to obtain the question in the statement. Now, let me multiply this function with this one. By the way, if your function is not continuous, there is a theorem telling you that your function is not differentiable there. Is not differentiable. Okay, let me also put this theorem as a recall here. Recall, this is a very useful theorem telling us that if your function is not continuous, then you can directly conclude that it is not differentiable, okay? This is a very useful function. So here our function is not continuous, so directly it is not differentiable at the given point origin. Okay. By the way, this is a theorem. So let's make our function a bit more complicated like this by multiplying with x. Now let me draw the graph of it. This time we are dealing with this function. Let me do it. If x is different than 0, it is defined like that. If x is 0, let's define it as 0. So this time I need to draw these lines. These are lines y equals x and y equals -x. I will draw the same curve, but now I need to draw it between these two lines. These two lines bounds my curve now. If you multiply by x, this happens. Your curve will do the same kind of behavior. Sine 1 over x has its own type of behavior, like wild oscillation around origin. I will draw the same thing, but between these two lines. Okay, let's try it like that. You see, I am trying to draw again a wild oscillation around origin, but since my curve is bounded with these two lines, I cannot jump from +1 to -1 anymore, because these two lines bound my curve. So that now, is there a limit at the origin? What do you think? In the previous case, the oscillations are not bounded. We do not squeeze them towards 0. So limit does not exist. But this time, what happens at the origin in terms of the limit? As x goes to 0, this function, x sine 1 over x. What do you think? What is this limit? This time limit exists, you see, because the oscillations are kind of controlled and we are pushing the oscillations towards 0. So limit exists. There is a unique number such to which your function, the values of your function are approaching around origin. At the origin, they get closer and closer to 0, of course. So what about the value of your function? Limit exists, it is 0, and the value of your function is defined as 0. Let's call this function as h of x. So this is the same as the value of h function. If this holds, then you can conclude that this function h of x is continuous at the origin, right? H of x is continuous at x equals 0. So that is what I wanted to recall you. Now, we can move one step further to study this function now, not multiplied by x, but x squared. Is it okay so far? So good? Any questions?
No, teacher, thank you.
Okay, so since this equality holds, limit is the same as the value of your function itself, you can conclude that it is continuous. Now, after covering the simpler cases, now we can deal with our own example 33, x squared sine 1 over x. F of x is given as x squared sine 1 over x. And if x is 0, it is given as 0. What I want to answer? I want to answer that is this function, is f differentiable at x equals 0? This is the same thing as asking whether this exists or not. Okay, these are the same question. So, to check differentiability, you need to check continuity first. Why? Because of this theorem. If it is not continuous, you can directly conclude that it is not differentiable. That's why to check differentiability, we need to start by checking continuity first. Check continuity at x equals 0 first. Okay? So how to check that? Just like we did above, we can check continuity. Okay, let me use again some geometric arguments to show you that limit exists as 0. Instead of multiplying with x, which affects the graph like this by bounding the curve between x and minus x line, now we are multiplying with x squared. That's why the curve will be bounded between these two curves, x squared and y equals minus x squared. Now, here is the graph. The same kind of oscillation will happen. Your curve will try to oscillate widely around origin, but we don't let it this time because it has to be between these two curves. It has to be controlled like this. We push the curve to get closer and closer to 0 around origin. That's why there is no more wide oscillation at the origin and the limit exists, right? So what about the limit at origin now? Limit of this function x squared sine 1 over x as x goes to 0 is what? As you can see, this value is forced to be 0 around origin. This is the graph of sine 1 over x, by the way. Okay, this is 0. And what about the value of your function at 0? It is also defined as 0, you see? Since they are the same, limit and the value of the function is the same, which means that now you can conclude that f of x is continuous at x equals 0. Okay, continuity is checked. If it is continuous, now you can continue with checking differentiability. A continuous function may or may not be differentiable at the given point. You need to check it. Now, we are ready to check differentiability at x equals 0. So how can you understand whether this value exists or not? What should I do now? I will use the limit definition, of course. So limit as h goes to 0, f0 plus h minus f of 0 divided by 0. Let me let me warn you about something. If your function is piecewise defined like this, and if you are searching for the first derivative at this breaking point like x equals 0, this is the critical point of this piecewise defined function, you need to use the limit definition, okay? To compute this, use limit definition. You have to use limit definition. Have to use limit definition. You cannot just tell, okay, this is a constant function 0, derivative of a constant 0 is 0. No, this is completely wrong. You have to find out the result by using the limit definition, by computing the result of this limit. Okay, let's move on then. This is f of h. What is it? Here, h goes to 0 means that you never touch 0. H never becomes 0. You just get closer to it. That's why you will use this part of the definition, h squared sine 1 over x. Okay, this is computed as h squared sine 1 over h. F of 0 is given as 0, right? So what we have here is limit h goes to 0, h squared sine 1 over h divided by h. Then simplify. So what you have done, limit as h goes to 0, h times sine 1 over h. What is this limit? Do you remember? We already covered it here. H times sine 1 over h. This is the graph of it. Okay, this is the graph of x times sine 1 over x. And the limit of it around origin is 0 by looking at this graph. This limit is 0. Also, if you don't have the graph, you can prove that the limit is 0 by using sandwich theorem. How do you use it here? If you don't have the graph, sandwich theorem, you know, sine 1 over h as a sine function is between -1 and 1. Now, I will multiply everywhere with h, okay? H times. Okay, first you can assume that h is positive, then you can assume that h is negative. You will have the similar computations. If I assume h is positive, I mean right-hand side, left-hand side limits, you should write it differently. So if you have such inequalities and send h to 0 from right, for example, you will have 0. So what does this mean by sandwich theorem? Upper and lower bound goes to the same limiting value, meaning that limit of the middle function has to be the same. This has to be the same. And you can also do a similar discussion for h goes to 0 from left, okay? So let me just remove this one-sided notation. You can write it in more details by yourself by dividing into two cases. So by sandwich theorem, it is doing like it is done like that. So limit is 0. What about, and what does this mean then? The result of this limit gives you the value of the first derivative. So this is the first derivative of the function. So the slope exists as 0. Okay, let's write some conclusions here. F prime 0 is 0, meaning that the slope of the tangent line is what? Is 0. If the slope of the tangent line, what kind line is 0? What kind of tangent line is this? What sort of lines has slope 0? So we have a horizontal tangent line, okay? The tangent line is horizontal. So we answered the question. The question was, does this function have a tangent line at the origin? We computed the first derivative, find the slope as 0, which means there is a well-defined slope, there is a well-defined tangent line. Even it is a very special tangent line with slope 0, it is a horizontal one, okay? So let's move on. Any questions now about this solution? Let me show it to you. To check the differentiability, to find out what this value is, we first check continuity. After seeing that your function is continuous at the origin, then, only then, you can check differentiability by using this limit definition. This limit turns out to be 0, so the slope is 0, so there is a horizontal tangent line there. Okay? Okay, before the break, I also want to solve this one, 34. The same question for the different function. Okay. 34. G of x is given as x sine 1 over x if x is different than 0. If x is 0, it is 0. We already discussed the continuity of this function at origin, right? The same question applies here. Let me show you the statement. Does this graph have a tangent line or at origin? So the same question, we need to search for the first derivative to see whether there is a tangent line or not. And to check differentiability, the question is g of x differentiable at x equals 0, asking the same thing, whether this exists or not. Okay, to check differentiability, we start by checking continuity, right? Check continuity at x equals 0 first. How do you check that? You compute the limit. Limit of this function as x goes to 0, limit as x goes to 0. I will use this part of the definition because x never touches 0 here. And I already showed you by the graph that this limit is 0. Also, by using sandwich theorem, I also explained it here. You can prove that this limit is 0. And as you can see, it is the same as the evaluated value itself. So this function is continuous. It's continuous at x equals 0. If it is continuous, then you can talk about differentiability. Now let's check the differentiability. At x equals 0. Okay, so I want to find whether this value exists or not. So to understand whether it exists or not, you need to use the limit definition of the first derivative. G of 0 divided by h. What is g of h? H goes to 0 but never touches 0. That's why we will use this part of the definition. G of h is h times sine 1 over h. G of 0 is just 0. Then what you have is the following. Okay, limit as h goes to 0, I have h sine 1 over h divided by h. This is what we have. Can simplify, and now we are ready to see the result. What do you think? What is the result of this? Sine 1 over h as h goes to 0. As h goes to 0, this part goes to where? This part goes to 1 over 0 is infinite. And what do you think? What is sine infinity? What is it? What kind of thing is this? Does this limit exist as a finite real number, or it does not exist? What do you think?
Undefined.
Yes, exactly. Let me justify you why this limit does not exist. Sine infinite is something which does not exist, okay? This limit does not exist because, you know, sine function is an oscillating function like this over the whole real numbers between +1 and -1. This is sine x function. As x goes to infinity, do you see any finite real value of sine x towards which, let me tell it again. As x goes to infinity, is there a unique number to which sine x approaches? No, you see this continues to do this oscillation behavior infinitely many times. So as x goes to infinity, there is no finite real number to which your function gets closer. So that's why this limit does not exist. Okay, if this limit does not exist, what is your conclusion? Does this function differentiable at origin or not? What do you think? Is it differentiable or not? Since you don't have a finite value here,
Not differentiable.
Exactly, is not differentiable, so slope is not well defined. So there is no tangent line at the origin, okay? This time the answer is no, there is no tangent line. Any questions about this solution? Okay, we first check continuity. If the question is about differentiability, checking the differentiability, you have to first check the continuity because your function cannot be differentiable without being continuity. If it is continuous, it may be differentiable or not. Then after checking continuity, you can check differentiability. If continuity would fail here, you would directly conclude that this function is not differentiable there, okay? If it is continuous, then it may be differentiable or not. You need to check it. Okay, before the break, let me also show you this question, then we will take a nice break. Okay, the answer for this one is really quick. Is there a vertical tangent line at origin? Again, the question is about differentiability, whether this exists or not, or whether your function is differentiable at origin or not. Is u of x differentiable at x equals 0? Or you can paraphrase this question whether this exists or not, right? Okay, that's why we need to first check continuity at x equals 0. How do you check that? You know, this is a step function type. If x is less than 0, it is defined as 0. If x is greater than or equal to 0, it is given as 1. You see, there is a jump at the origin. So the limit here, limit of this function as x goes to 0, what do you think about this limit? Left-hand side and right-hand side limits are different. This is the graph of u of x, by the way. Since one-sided limits are different, this limit does not exist. Meaning that, is it continuous or not? Is obviously not continuous at x equals 0. If it is not continuous, there is a theorem saying that it is directly not differentiable, okay? If not continuous, there is nothing to do. It is directly not differentiable. This is a theorem. If it would be continuous, we would continue checking differentiability. It may or may not be differentiable then, but if it is not continuous, for sure it will not be differentiable, okay? So, not differentiable means that this does not exist, so no tangent line at the origin. Okay? Any questions about the solution? Okay, no questions.